The last speaker of this afternoon is Professor Yoshikazu Giga from the University of Tokyo. Professor Giga is from the same city and obtained his PhD at the University of Tokyo in 1981 under the supervision of Professor Fujiwara, and soon later his Doctor of Science degree there. In his early career, he worked in the United States, in particular in the Courant Institute. After returning to Japan, he served as a full professor in Hokkaido University, and from 2004, he is a professor at the University of Tokyo. Professor Giga is a highly regarded Japanese researcher who has had a number of contributions to Japanese mathematics that have been recognized by numerous prizes. In particular, a few years ago, Professor Giga was awarded by the government of Japan a Medal of Honor with purple ribbon, and for his dedication to development of Japanese mathematics and his research. Professor Giga is a world-leading expert in analysis of nonlinear parabolic partial differential equations, and his interests include Navier-Stokes equations, semi-linear heat equations, surface evolution equations, and singular diffusion equations, and in particular using viscosity solution for their study. So today, Professor Giga will give a talk on the large time behavior of growth by birth and spread. You have the floor, Professor Giga. Thank you.
Okay. First of all, I would like to thank scientific committee for inviting me to this meeting. Today, I'm going to talk on large time behavior of some nonlinear parabolic equations coming from material science, crystal growth problem. And of course, large time behavior solution is always an important topic in partial differential equations, especially evolution type and especially parabolic type. However, you'll see this is not well understood if the parabolicity or diffusion is degenerate. I would like to give one simple looking example today. This is very simple looking, but the problem is not yet solved. Okay, so this is Okay, here is my plan of the talk. The first, I give a model, explain the model, and explain the problem. And the second, I would like to discuss some couple of explicit solutions and a special case, which we can understand quite easily. And then next, we'd like to study large time behavior, especially some growth rate of the solution. And last, we give some open problems. Okay. Okay. And when you talk about crystal surface, this is some fact, crystal surface will grow by catching other atoms from above, other atom molecules. And it is believed that there are two mechanisms called two-dimensional nucleation and spiral growth. And if the crystal surface is very perfectly flat, we know that two-dimensional nucleation dominate. So what is two-dimensional nucleation? I would like to say, okay, a flat crystal surface grow by catching other atoms. And so the problem is how should the model? And of course, there are several models, and the typical one is called birth and spread model, and it's already found in the famous book by O'Hara and Reid in 1973. Okay, this is a schematic picture, and here's a crystal surface, and here's the crystal surface. Yes, and this is the other atom, and the other atom, crystal surface catch other atom, and it grows. So it looks very simple. And there are many birth and spread model, in fact. But what I mentioned here is very simple birth and spread model. And at the atom, so the E is a set, E is a set, which is called a set of nucleation centers. This is a place where the crystal surface easily catch other atoms. Other place it's difficult. So it's something like defect place, something like that. And then, and this is an atom molecule. And its height h is the size of molecule. So this model, in some sense, macroscopic in horizontal direction, but microscopic in the above. So this is the mechanism of burst. It's very simple. And what do when spread? Spreading is spread is something like this. Is this baby stuff is spread by catching other atoms from horizontal directions. And the law of growth law is written in this form. Velocity, normal velocity of curve is given as this function, and v infinity is fixed, and rho zero is also fixed. Can be zero actually, but h is the curvature of this curve surrounding this curve, and 1 is 1. Yes, so this is a spreading law. And you see, if rho c is identical to 0, this is kind of Huygens principle or Eikonal equation, just propagate in constant speed. So this is spreading law. And here's the curvature effect is in. And actually, this equation is known as a Eikonal curvature flow equation. Yes. And it can be formulated in the hypersurface in Rn. And normal velocity of this hypersurface is given as a mean curvature plus constant. And this is what is called Eikonal curvature flow equation, because if rho c is equal to 0, that's Eikonal equation. So this is often called Eikonal curvature equation, or curvature flow equation with driving force. Here H is anyhow mean curvature for gamma t. Gamma t is evolving surface. And in our previous example, this is an Eikonal curvature equation in the plane. So gamma t is just a curve. Okay? And it is easy if you consider the initial data, something like circle of radius r0. Then the equation I write is just ordinary differential equation, and it stays. If this radius is a critical radius, then the solution stays. It doesn't move at all. It doesn't grow at all. But if this is less than this critical radius, this shrinks to a point in finite time, like mean curvature flow. But if it's bigger than critical size, it expand, and it tends to infinity. So this is very simple. If you write ODE, you can easily see this kind of property. Okay, now let's go back to burst and spread model. So the step 1 is burst, and step 2 is spread. And step 3 is actually second burst here on E. And yes, step 4 is another spread. And step 5 is another burst. So that's the reason we would like to say spread and burst and spread model. So burst is just on E. The other place is just spread with the velocity, with the spreading law. Okay. And it is very interesting to describe the spreading law by the height function. So consider the each level set of the height function spread by the Eikonal curvature flow equation of the form. Then the height function solves this equation, u sub t over du. Du is gradient, spatial gradient. So you will see this is just n, normal velocity, normal of each level set. And this divergence is nothing but mean curvature of normal of each level set. And this is the normal velocity of the level set. So this is called level set equation, or iconal curvature flow equation. And this equation is very helpful to define the generalized solution for the mean curvature, iconal curvature flow equation after it develops singularities. So this is such thing is based on such level set equation. I just briefly recall such notion. By adjusting the notion of viscosity solution, we are able to solve the initial value problem with this level set equation in Rn globally in time. So each level set only depends upon the initial level set. So this is a very interesting equation. You see, this equation has highly degeneracy from the point of parabolicity because this equation has no diffusion orthogonal to each level set. So there's no diffusion orthogonal to each level set. So we need some weak notion to solve. So that's the reason I say viscosity solution. And as you know, the notion of viscosity solution was introduced by a long time ago by Crandall and Lyons and developed by Evans and Ishii. So this is very suitable for such problem. So you can use this level set equation to define the general solution for such kind of equation, because the equation the solution may have singularities. And here's some history of the level set method, and it has been established a long time ago in the last century. And here I mention a little bit about new things because if you talk about material science, anisotropy is often very important. And especially equilibrium shape is may not be a circle or ball, maybe some roof shape. So it's kind of anisotropic stuff. And the roof shape can have a flat portion. If the roof shape has a flat portion, it means it's a equation should be something like equation with non-local effect. So it's difficult to study. So that's the reason it takes quite a long time to reach interesting result. So this roof shape was mentioned in the introduction of Professor Caffarelli of introduction by Caffarelli of Professor Figari, right? So roof shape, if you talk about roof shape, this kind of study is quite important. But I think it takes 1 more hour to describe such kind of things, so we skip completely. I wrote it in a proceeding, but I would like to skip completely today. So now we go back to our PD model. Okay, our PD model is the following. First, we have the burst, so burst and spread. And if you do the alternatively and make the time degree tends to 0, eventually you get such kind of equation. So this is a kind of parabolic equation, but now you have some driving force term. So this is different from usual level set equation, right? So we are interested in this problem. Okay, good. No. So this is our problem, okay? We consider this equation. So this du dt time derivative is equals to this quantity, right? And the initial data is just flat, perfectly flat. U is the height function. And the question we would like to discuss is what is the large time behavior of U? For example, investigate asymptotic speed or growth rate. This type of problem is very important, very important in crystal growth. We would like to measure how the crystal grows, how the crystal grow. So we'd like to answer such kind of question. So if you talk about, in the case of our rho c is equal to 0, then our equation is nothing to do with the Eichner equation with deriving with source term. Okay? And the equation that just becomes a very simple form. And as you expected, the solution is such of this form. So something like, suppose E is just point, and then the solution is just simply growing in this way. So it's very simple. It's spread, but growing. So apparently this is just growing. So this is general form. And of course, if your nucleation center is just one point, a discrete point, you need to extend the notion of viscosity solution. Otherwise, there are many solutions. But even we introduce viscosity solution, it's not enough. So we need to take some envelope solution. But anyhow, we need the notion of viscosity solution. We need, and we have to think something like maximum viscosity solution in this setting. But anyhow, without knowing the notion of a solution, people can expect a solution. Okay. It doesn't work. Suddenly it doesn't work. Yes? It's work. Okay. So here's another example. So this example, spreading rho is the same speed, but there are many nuclear centers, but the weight is different. Speed is different. And the expected envelope solution is of this form. And this is already proposed by Schulze and Kohn long time ago, but without definition of solution. So this is the solution. So each nuclear center, they form some mountain like that. And you'll see asymptotic speed, or speed becomes maximum of the CI. So if you have a small nucleation source, it can be dominated, and eventually strongest one remains. So this is a very important observation. And I skip this few lines. It's a little bit technical. Okay. So what is asymptotic speed for this problem? So suppose that R is non-negative and R is a compact support. Then what we know is if you rescale, this is, I think, a hyperbolic scale. If you rescale U lambda, then this rescale profile equals exactly what we see in the problem with just one point source. So R is actually growth rate, or actually asymptotic speed. And in this case, R is just maximum of R, little r. So the strongest part completely determines the speed of this source. This is asymptotic speed. So R is just maximal R. And my point is this kind of phenomena, this kind of stuff, still okay for our full model. However, important thing is that this R may not be a maximum of R. So because of curvature effect. So that's my point. And I would like to explain by much more examples. Okay. And there's another problem, of course. When I mean the asymptotic profile, we rescale, right? But this is an unrescaled version of asymptotic profile. And this is much more naive. But the problem is more difficult. Okay. So in this case, find R, this is asymptotic speed, and W is unscaled asymptotic profile. So U is asymptotic. This says U is asymptotically equal to RT plus W. So this is a way. So our question is find R and W such that this holds. Okay. And if you do the formal argument, you see that R must be a derivative of time derivative, sorry. And W must satisfy this one. And the question is find R and W. For periodic case, such R and W is known to exist. It goes back to the work of Namaha, Rocco-Joffrey, and Fatih. And the feature problem, especially here in Brazil, there are very strong group in dynamical system. And this is, there's a theory by weak CAM theory. And what they say is R is uniquely determined, provided that weak comparison principle holds. Weak comparison principle means if it's a strict subsolution and if strict subsolution and strict subsolution must stay below the super solution, something like that statement. So if R is uniquely determined anyhow. However, W is not uniquely determined. This is the point, even up to additive constant. Right. So this is a feature of problem. Okay, we will see. Yeah, here's the example. And suppose that consider one-dimensional problem, and suppose that the nucleation force is just 2 points or periodically distributed, but 1/4 and 3/4. And consider this very simple equation, one-dimensional equation, right? And then the third problem, what I mentioned is this equation. And IE is just 1 and 2 point, and otherwise this is 0, okay? This is what is, and this set is often called Aubry set. Aubry set is 2 points, right? Aubry set is actually, in this case, a projected Aubry set in the dynamical system, but it is in this particular case, this is just equilibrium set. Okay, and you see, consider the periodic problem, and you see even if viscosity solution, the viscosity solution not unique even up to constant. And actually, asymptotic profile is chosen by initial data, and W is determined by the value at Aubry set. So I just give you the definition of viscous solution for this particular case. It's very easy to understand. We say the function U is the viscosity subsolution of F minus this equation. If whenever phi and x hat, this is test function touching from above, satisfies this inequality. And F star, sub star means lower semiconductor envelope. A supersolution defined in a symmetric way, and viscosity solution is nothing but viscosity sub and super solution. So in the case f of x is 1 minus 1e, local maximum cannot be attained except e to be a subsolution. So this is this stuff is only situation only in the set E. So go back to this slide. You see the solution can take minimum because it is still viscous solution any place, but the local maximum can take only on this point. The other place, anyhow, the solution, the derivative must be 1, so slope is 1. Absolute value of slope is 1. And but here you can take local maximum. So you may take this value if you like. You may take other value if you like. So you will see infinity many solutions. But if you determine these two value, right, then the solution is actually unique. So this is the structure of the problem. Okay, now I'm going to talk about spherical symmetric case, what happens. So now rho C is now 1 for simplicity, but infinity is just 1. And consider level set of equation, diagonal curvature equation with source term, Rx. Okay? And what happens? And suddenly this does not work. Yes, we would like to see what kind of solution it behaves. Could you help? Oh, yes. So R is assumed to be positive, non-negative, and support is compact. U0 is continuous, and support is also compact. And the basic property is, of course, if R is discontinuous, even if R is discontinuous, there's a global solution, but which may not be unique. Of course, weak comparison principle holds. Of course, if R is smooth, Lipschitz is continuous, the solution exists, it's unique. And the spherical symmetric case equation is reduced to the linear equation. And the linear equation in the world of viscosity solution is difficult to handle sometimes. And this is the case. And the source term is this is a nucleus. Source term is a characteristic function of Bohr. Okay, and this is the okay. And if so, this is the n-dimensional thing we consider. If R0 is less than critical, then the growth is completed in finite time. And if the R is greater than this constant, the growth rate equals to C. So its growth rate is equals asymptotic speed is equal to C. And if R0 is n-1 exactly, then it is very trivial, but U is just T times this characteristic function. So it turns out, yes, the speed C, this is growing speed is a C in the ball, but never grows outside. So this is the first order equation, but not coercive in the sense that F does not tend to minus infinity as mod P tends to infinity, so because of linear. So this non-coercive type is difficult, by the way. It becomes slower and slower. Okay, this is the solution. Yes, and if the rho zero is small, so the nuclear center is small, then the growth stops in finite time, actually. And if this is yes, if it's big, then the speed is C, so asymptotic speed is C, and this is okay. This is what we want to say. Okay, so it depends upon how big the nucleation center is. So it doesn't work so much. Now it works too much. Okay, so we would like to study the existence of growth rate. Okay, and how to prove the existence of growth rate, existence of asymptotic speed for the general problem. And we missed one previous slide, but it takes some time to go back, so I don't want to do that. So first thing we observe that if your solution U, suppose you have a solution U, and take maximum value, and then we see this maximal value has a subadditivity property. So this is actually easy to prove. I will show you. And we set U is a difference, let V is a difference between the profile of height function U at T time T plus S and phi of S. So this is mass. Of course, at the beginning, this is, by definition, V is less than 0 initially. By comparison, V is equal to always less than U, which implies this inequality. And taking sup, you get this inequality. So this is subadditive. And once you get subadditivity, then we get growth rate. Because there's a Fekete lemma, and if the function is subadditive, then phi of t over t is actually non-increasing. So the limit always exists, and this is a fixed. This value is determined. So actually, for example, if you prove the Lipschitz bounds, then we are done, essentially done. So, and actually this is true. And once you have the Lipschitz bound, as I mentioned here, maximum point, suppose that maximum point is satisfied. Okay, first of all, we have to notice maximum point of x of t, of u, of t, is always inside the convex hull of support R. Thus, by combining Lipschitz bound and behavior of phi maximum value gives the desired result. And this argument, similar argument, is found in the lecture note by Gilbert for the different situation. But this is essentially similar. And to get Lipschitz bound, we use Bernstein argument. This is often used. So I would like to skip it. This is yes. And then I would jump to estimate of asymptotic speed. And the problem is, if R is, for example, the constant multiple of characteristic function, is it possible to prove such kind of intermediate speed or not? What is such kind of intermediate speed exists? Of course, when E is the set of nuclear center is a ball, we have these two situations we already found, but the question whether they're intermediate. And actually, the answer is yes. The example is just considered square in the plane. Okay, and by simple comparison, if D is 2D is a square of side length 2D. Right. And if the D is small, so that this circle is a critical circle, smaller than critical circle, as you imagine, there's no way to grow, because in the critical surface case, the solution does not grow. At least outside it doesn't grow. So, and if D is bigger than 1, so that it includes critical circle, then it grows, and the speed is, since the speed of this, in the case of critical greater than critical surface is equal to C, the maximum speed, this must be grow the similar way. So the question is what happens in between. And the situation, okay. And actually, what we would like to claim is there's intermediate speed. And this is one of our main theory. And suppose that D is less than 1 and bigger than this constant, so then there exists in-between speed. So in this case, if your external source term is discontinuous, we cannot apply previous theory saying that asymptotic speed exists. it doesn't work for this problem because source term is singular. But anyhow, you see this intermediate speed exists. And you see the growth speed seriously depends upon shape of E, source term, not just maximal time, maximum. So how do we prove for such kind of things? Okay, we consider this equation, and the important set is the place, the set where U is equal to CT. U star is a soup envelope, as upper semiconductor envelope. But this set plays an important role. And it turns out this A max is, in some sense, set theoretic solution of the mean Eikonal curvature flow equation. Set theoretic actually sub-solution, set theoretic sub-solution. So in some sense, this is a viscous sub-solution of this equation. And what is important is A max is always in the set of E. Actually, this is a solution of obstacle problem. So mean curvature flow, Eikonal curvature flow with obstacle. And what is the idea of proof? Okay, I think it is easy to see that U is a sub-solution, A is a set theoretic sub-solution. Yes. And what is the difficult? What is, of course, what is also easy, but so I show you the proof of this stuff. The set A max is always in E. If not, there's a point x0 such that it belongs to A max but outside E or some t. Then of course, the function CT is a function, a test function of U from above, but this gives a contradiction because C is becoming negative by this. So this is easy consequence. So if the such kind of top disappear, and then the speed is less than this B, less than this C. And it's not difficult to see, but yeah. So this asymptotic speed is supposed to be less than C. So this is not difficult to prove, I will just skip it. So the question is whether this A max, set A max disappear or not. And this is actually possible by constructing explicit super solution to push. Yeah, so this is okay, kind of super solution, a set of similar super solution pushing everything inside. And this such kind of such kind of super solution exists. And for some time, the set A max becomes empty. So this is actually case. Yeah, this is the way to construct such kind of super solution by from the point of obstacle problem. So maybe it's better to skip it. And anyhow, using disappearance of A max in finite time and applying theorem 4.4 yields upper bound for you. And the lower bound is not the same, but similarly we can construct by constructing sub-solutions. So it's time to give a summary. So I would like to say even second order burst and spread model, we proved the existence of asymptotic speed provided that external force term or source term is Lipschitz continuous. We need Lipschitz continuity. And the second statement is we proved the asymptotic speed may not be equal to the maximum of source term, which is quite different from the first order model. However, of course, there are many open problems. If we talk about asymptotic expansion, this is asymptotic expansion. By Lipschitz bound, we know if you take subsequences, we know this one. But full convergence is completely left open. So R is, of course, asymptotic speed. So we know the convergence in problem 1. If we take a subsequence Tj, of course, this is uniform Lipschitz, so Ascoli-Arcera, you can prove such kind of sequential convergence, and the limit satisfied cell problem. But of course, as you see, even first-order model, asymptotic profile W may depend upon subsequence. So what is the uniqueness set? And clarify the dependence of W with respect to initial data U0. Initial data choose such kind of W we expect in the first-order experience. In the periodic setting, this problem is well studied for the first-order equations. Going back to Namuha and Rocco-Jofferi and Fati and Barnes and Suganis and Professor Ishii in many situations. Professor Ishii's work is for Rn. But anyhow, this is the first-order case. The second-order degenerate parabola problem is difficult to handle, as I mentioned, and there's a study by Cagnati and Gomez and Mitake and Tran based on a joint method by Craig Evans. But however, it applies to the kind of this equation, Hamilton-Jacobi equation with diffusion term, and A over X can be 0, non-negative. This is by taking a joint. This it works. So the second-order problem only studied in this case if the problem is degenerate. So in our degenerate problem, it doesn't apply at all. So completely new idea is necessary. So full convergence problem is a very interesting problem, and it's not yet studied. And another interesting question is, what is asymptotic speed? If R is discontinuous, we know we prove that asymptotic speed exists if R is Lipschitz continuous. But in general, if R is just discontinuous, like characteristic function, we don't know the answer. And of course, it's a good problem to study how R depends upon little r, quantitatively and qualitatively. For example, does it depend on R continuously or not? So far we know this asymptotic speed, R depends on little r monotonically if it exists. So this is the two important open problems. And I wrote other open problem in proceedings, but it's better not to mention here. And and we conclude my lecture by mentioning another problem, very related, called spiral growth. Yes, spiral growth problem, studied by Otsuka and Tsai and myself. And this is a kind of a little bit different mechanism compared with two-dimensional nucleation. But it is again, the surface phenomena. And the surface is growing some speed, and people are interested to predict the speed by model. And here is a lot of numerical study, couple of numerical study done by ourselves. And I think we conclude my lecture by showing this slide. And this is, in some sense, each level set moves by the Eichner curvature flow equation, but it's a kind of spiral center somewhere. This is two spirals and collide and each other and form such kind of things. And this is more popular in the world of crystal growth. And this is calculated by a modified level set method introduced by Otsuka, my former student. And this is a spiral growth. So I think we conclude this talk by showing this one. And we conclude this talk, I'd like to say that although there are a lot of studies for large-time behavior, even a very simple problem left open completely. And I would like to advise young people to find the problem in the very real phenomena, and it often find another mathematics. So this is interesting. So thank you very much for listening, and I would like to return this slide and my missing slide. So thank you very much. I'm missing.
Thank you very much, Professor Giga, for the nice talk. Are there any questions? Please. Don't be shy. Any questions, please? Okay, so if there are no questions, let's thank Professor Giga again.